Good morning, chemistry students. This is Mrs. Krumscheider, and we are starting with our notes over Chapter 8 about chemical reactions. You'll see on your outline that we start with a review. Again, it's under review for the law of conservation of mass because normally we would have done Chapter 7 before we did Chapter 8. So we're going to go over the definition of the law of conservation of mass, which is that mass can be neither created nor destroyed in an ordinary chemical or physical process. We will see that when we get into Chapter 7, that this will mean that the mass of our reactants, or actually even, it's going to happen even in this chapter, sorry, okay, that the mass of our reactants has to equal the mass of our products. So we're going to be talking about chemical reactions, and in chemical reactions we're going to have reactants and we're going to have products, and the mass of the reactants has to equal the mass of the products. Don't worry, we're not going to have to do math to do this because you're going to be what I tend to call atom counters, because the mass of an atom doesn't change. Instead of having to do math to see that we've followed the law of conservation of mass, we will simply be able to count atoms. So you guys will be atom counters. So again, for the law of conservation of mass, this is really a little preview. We will be using this law throughout Chapter 8 as you learn to balance chemical equations. The next topic for review is an important one. This comes from Chapter 6. So if you're struggling with this and you have your outline, you could take a look back at Chapter 6 to help you remember these things. Again, this is something you have to be able to do well. So the reason that this molecular compound and ionic compound information is on this review is because if you cannot correctly write the formula for an ionic or molecular compound, you will not be able to correctly write and balance a chemical equation. So, as a means of review, we'll start by talking about molecular compounds. Hopefully, when I ask you the question, what is a molecular compound made of, you are able to answer that on your own. A molecular compound is made of, for our purposes, remember, two nonmetals. Remember, nonmetals are, looking at your periodic table, they are to the right and above that heavy stair-step line. Those are our nonmetals. So we're going to know a molecular that we're doing something with a molecular compound when we see that our compound is made of two nonmetals. So if you're given the formula, how do you write the name? For example, PCl5. Okay? So remember, when we're given the formula and we do the name, hopefully again you remember how we do this. The subscripts become prefixes. So remember we said subscripts equal prefixes. Now again, you don't have to have those prefixes memorized. You have your helper sheet and it has the prefixes on there. Okay, so our subscripts become prefixes and our second element has to end in "ide." You won't be doing this a whole lot, okay? That's why I have this. That's why I have this highlighted right here, because this is pretty important, and why I have this highlighted, because this is pretty important. You won't very often have to be given the formula and asked to write the name. So coming back to this example over here, the PCl5, so this would be, because there's no subscript here, we can use mono, or remember we can leave mono off on the first element. So, and then the 5 means tetra. So this is monophosphorus tetrachloride, or we can just call it phosphorus tetrachloride. Either works. Okay? All right, more importantly, when you're given the name, to write the formula. Again, this is more what you will be asked to do frequently. So if we have dinitrogen, dihydride, okay. This is more often what you're going to have to do throughout Chapter 8 is, given the name, write the formula. So again, remember here, we just take that subscripts equals prefixes and we kind of flip it around and we say that the prefixes equal our subscripts. Okay, so dinitrogen dihydride means, because we have di, that means our subscript is going to be 2. So this is N2H2. Don't know if that compound exists, but it works for an example. So again, the idea here is, remember, for molecular compounds, the part that's really important is, again, these parts that I've underlined and highlighted. You need to be able to identify that a molecular compound is a molecular compound because it's made of 2 nonmetals. And once you know it's made of 2 nonmetals, then when you're given the formula, you need to be able to write the name, which means you're going to have your prefixes become your subscripts. Remember, with molecular compounds, there's nothing to do with charges. No charges at all with molecular compounds. All right. Again, moving on to ionic compounds. Again, hopefully, again, this is in Chapter 6 if you need to kind of go back and look things over or reread some things in your textbook. But ionic compound, again, hopefully when I ask that question, what is an ionic compound made of, you're able to answer that. Remember, we say that ionic compounds are made of a metal and a nonmetal. We also say our other thing is, or remember, they have a polyatomic ion in them. Okay? So again, to know that an ionic compound is, or a compound is an ionic compound, you're going to look for it to have a metal and a nonmetal, or it has a polyatomic ion in it. Again, remember that metals are to the left and below the heavy stair-step line on the periodic table. Nonmetals are to the right and above that heavy stair-step line. Polyatomic ions, you have a list of 10 that you're supposed to have memorized. And then the rest of the polyatomic ions that you're likely to encounter in chemistry are on your helper sheet. So again, You need to know, be able to look at a compound and identify that it's made of a metal and a nonmetal, or it has a polyatomic ion in it. Again, not as often in this chapter you have to do this, but if you're given the name, about writing the formula. So how about tin to hydroxide? Okay, so again, you don't have to do this quite as often, and you have a flow chart that you made back in chapter 6 with this. Remember that first question is whether or not this compound is ionic or molecular. We know that this compound is ionic because it's made of a metal in it. And when we want to say kind of generically what we're going to do, sorry, I messed that up, didn't I? I did the wrong thing. So let me erase that. Sorry about that. We're doing the other way. So this is, we want to start with when I give you the formula. So let's say that it is Fe2O3. Sorry about that. Okay, so generically, if we're given the formula and we have to name it, remember our generic way of talking about this is that we're going to combine the name of the cation and the anion. Okay, so remember, one of the things we have to be careful about is that with our cations, one of our questions was whether it was a tall or short column. That's on your flow chart that you made in chapter 6. Because remember, if it's in a short column, so it's a transition metal, it might have more than one possible charge. Okay, and if it had more than one possible charge, remember you had to name it twice, right? 2 times. Remember those 2 ways were the stock and the classical systems. Stock system, that was the one that we really prefer, because remember with the stock system we use a Roman numeral, and the Roman numeral is equal to the charge on the cation, the metal atom, or metal ion. With the classical system, remember we use those Latin roots, which are on your helper sheet, and then the 2 different suffixes, which are ic for the higher charged one and us for the lower charged one. Okay, so if we kind of work through that flow chart for this formula that I've given you here, right? So first off, our first question always is whether or not this is ionic or molecular. We know that this is an ionic compound because we have a metal in it, iron. Our next question then is, when we're dealing with an ionic compound, is our cation, is our metal in a tall column or short column? Well, iron's in a short column. So that means when iron is in our short column, that means we need to check our helper sheet. Is iron on our helper sheet? Yep, it is. It has more than one possible charge. Now remember, we have to figure out what that possible charge is. Okay, so remember to do that, we look at our anion and we say, oh, oxygen has a charge of -2 on the periodic table because it's in group 6A, and there's 3 of them, so we have a -6 charge here, which means I have to have a positive 6 charge here for my iron, and there are 2 of them, so that means my iron has a +3 charge. So now I'm able to name it with the stock system, right? The stock system name for this would be iron would be iron 3 oxide. And the classical iron 3 is the higher charged one, so iron is fair. It would get the ic ending oxide. Remember, if our metal only has one possible charge, then remember we don't have to do any Roman numerals or anything of that nature. That's only if it's in a short column. All right, again, however, the part of this that'll be more important is that when you're given the name, you write the formula. Okay, so again, this is more what you're going to have to do. So we'll kind of do that same example I had, that tin 2 hydroxide. Okay. And again, this is where you had those 4 steps. Hopefully you remember those 4 steps. I don't have room to write them all down, but they should be automatic here, right? Our first step is we write our symbols. The second step is we write our charges. The third step is we crisscross. Remember, we're only crisscrossing the charge itself, not the positive or negative. So just the number, not the positive or negative. And then our last step is we make sure we have the simplest whole number ratio. So again, those 4 steps: symbols, charges, crisscross, lowest whole number ratio. Symbols, charges, crisscross, lowest whole number ratio. Again, symbols, we use our periodic table, okay? Charges, again, if the element is in a tall column of the periodic table, you should know its charge from where its position is on the periodic table. Remember, group 1A has a charge of +1, 2A +2, 3A, which is pretty much just aluminum and boron, have a +3, 5A has a -3, 6A has a -2, 7A has a -1. Okay, so you should know the charges for the tall columns based on where they are of the periodic table. Short columns underneath that heavy stair-step line, remember that's when you're checking your helper sheet. Okay, and again, depending upon whether the name uses the stock or the classical, if it uses the stock system, remember that just means that the Roman numeral is equal to the charge. With the classical system, you'll have to use your helper sheet and look at the 2 different charges that are there. Okay, so we've gone over symbols and charges, crisscross. Again, a reminder about crisscross. We're only crisscrossing the number from the charge, not the positive or negative. And when we crisscross, we have to remember if we have a polyatomic ion and we need more than one of them, you have to use parentheses. And then we always make sure it's the lowest whole number ratio. So if we go through those steps for this example here, remember again, our first question always is this compound ionic or molecular? We know this compound is ionic because tin's a metal, plus hydroxide is one of the polyatomic ions you're supposed to have memorized. So we know it's an ionic compound, which means we need symbols. So we use our periodic table. Our symbol for tin is SN. And again, its charge is +2 because that's what that Roman numeral is telling me when I have the stock system. My symbol for hydroxide that you have memorized is OH with a charge of -1. So I have my symbols, I have my charges, I'm ready to crisscross, right? So this 2 is going to come down here. But again, I have a polyatomic ion, so I need to put it in parentheses. And this 1 is going to come down here. So I write this as SN, OH in parentheses, outside my parentheses 2. And 1 to 2, that's the lowest whole number ratio, so I leave it that way. Again, the important part of this that we're going to be doing throughout this chapter, okay, is that you can identify whether a compound is ionic, okay, and mostly going to be given a formula and asked to write a name. So if you're comfortable with that, you'll be okay. Our next item for review is our diatomic molecules. Again, this is part of what you've been memorizing. These are these molecules that these never exist alone. They're always in a compound. So Oftentimes they'll be in ionic or molecular compounds, these diatomic molecules, okay? But if they're all by themselves and they're an element, they aren't by themselves. Remember, this is your Mr. Brinkelhoff. So this is hydrogen, there's 7 of them, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, so this will become very important as you learn how to write and balance chemical equations, because sometimes these are going to be a reactant. So it might say that one of our reactants is nitrogen all by itself. Okay, something we're reacting with. Well, when we go to write our formula for nitrogen, we have to write it as N2 because nitrogen never exists as a single atom. It's always going to exist bonded to another nitrogen atom. So the diatomic molecules are really important that you remember. Again, they are listed on the bottom of your helper sheet or of your polyatomic ions you have memorized. So they are there for you. So that kind of concludes the review portion of this. Moving on then to describing chemical change and word equations. Examples of word equations in real life. So again here, you have, or examples of it should be chemical equations in real life. So again, chemical equations and reactions happen around you all the time. If you think about that right now as I fix this, hopefully you can think of a couple things that are chemical reactions. Think about, there's lots of different ones. Basically, one of the foundations of a chemical reaction is that there's some sort of change. So, for example, the rust that forms on an automobile, that's an example of a chemical reaction. We know it's a chemical reaction because the part of the car that's not rusted looks different than the part of the car that is rusted. Okay. Your car has a lot of them, so the energy from your car battery, that's a chemical reaction. The combustion of your gasoline in your engine, that's a chemical reaction. You don't have gasoline coming out your tailpipe at the end. In your in biology class, photosynthesis is an example of a chemical reaction. When you cook, that's an example of a chemical reaction, right? The raw chicken that you start with looks way different than the chicken when it's cooked. Your raw steak looks different as a raw steak than it is when it's properly cooked. Your pork chops, okay? So anytime you see that change, you know that it's a chemical reaction. Another one, maybe a little bit more gross to think about, but the digestion of food is a chemical reaction, right? The food that goes in your body looks a little different when it comes out of your body. So that's an example, again, of a chemical reaction. Make sure you have a couple examples written down in your outline. So again, just kind of going through that list of ones I provided. Digesting food, photosynthesis, the energy from your car battery, the rust on a car, cooking your food. Those are all examples of chemical reactions in real life. One of the foundations of chemical reactions is that all chemical reactions involve changing the substances. Okay, so in chemical reactions, one or more substances, which are called the reactants, okay, change into one or more new substances. Which are called the products. To represent this change, we use an arrow. So an arrow is used to represent this change. So for example, again, we always have our reactants are always written on the left-hand side of our arrow, and our products are written on the right-hand side. Okay, so again, all chemical reactions involve changing substances. One or more of the substances that are called reactants, those are your starting substances, that's what you start with, change into one or more new substances, which are called the products. An arrow is used to represent this change, and again, an example of what we'll start to look at here is that we'll have the reactants on the left, our arrow, and our products on the right. In chemical reactions, okay, bonds are broken and new bonds form. So what's actually happening is in those starting substances, some of the bonds between atoms get broken and new bonds form between different atoms. So that's what's really happening in our chemical reaction. An important idea that kind of goes back to what we talked about in the review is that atoms are not created or destroyed. They are just rearranged. Okay, so this is, again, kind of that part of how you're going to become atom counters. The way that you're going to know that you have properly balanced a chemical equation is you're going to count and see, okay, that the number of atoms on the reactant side of the equation is equal to the number of atoms on the product side. And this is because of that law of conservation of mass. So that law of conservation of mass is why we can just count atoms to see that our chemical equation is balanced. So again, all chemical reactions involve changing substances. In a chemical reaction, bonds are broken and new bonds form. Atoms are not created or destroyed, they are just rearranged. You are going to become atom counters, and you're going to count and see that the number of atoms on the reactant side of an equation is equal to the number of atoms on the product side of an equation, and that's because of the law of conservation of mass. Sentences are representation of chemical reactions. Okay, so again, an example of this is that iron reacts with oxygen to produce iron 3 oxide. Also know it as, right, aka rust. Okay, so this is an example of a sentence representing a chemical reaction. Okay, iron reacts with oxygen to produce iron 3 oxide, also known as rust. Again, we're going to use this equation throughout our Chapter 8, Section 1 notes. Okay, so what do? where our goal here, remember, is to have a balanced chemical equation. So the first step is your textbook, your problems are going to give you a sentence. Now, this is a pretty short sentence. Sometimes they look more like a paragraph with a lot of extra information in them, okay? So the first thing we're going to do to get started on eventually writing a balanced chemical equation is we're going to write what's called a word equation. Your word equation is going to use a combination of symbols and words. Okay, so it uses both. The only symbols that you're going to see in a word equation, okay, are a plus sign and that arrow. Okay, so those are these two symbols right here. These are the only symbols that appear in a word equation. So, again, if we look at that example sentence that we just wrote, okay, so that iron reacts with oxygen to produce iron 3 oxide, also known as rust. So, the plus signs, okay, those are going to be your ands and reacts with. Okay, the arrow, quite a few different words are sometimes used for the arrow: produce, yield, making, any of those would work, okay? So when we kind of go back here to this word equation and we kind of look at it, right, reacts with, that's going to become a symbol. That's going to become our plus, okay? Oxygen to produce, okay, so to produce is going to become our arrow, okay? So that allows then our word equation for that reaction to become iron plus oxygen, arrow, iron, 3 oxide. Okay, so that's our word equation for that one. I'm going to give you 2 more examples that we'll do, and then we will be done. Okay, so here's another example. Our sentence is hydrogen peroxide I don't know if you guys can hear my cats fighting outside the door. Reacts to form water and oxygen gas. So you could pause your YouTube video and see if you could do this on your own. So again, the idea here is reacts, okay, is going to become a symbol along with the to form, and this and is going to become a symbol. Okay, so the word equation for this one is hydrogen peroxide, our arrow, water, plus oxygen. We can even leave the gas out because that's extra information that we really don't need. So the purpose of a word equation that you might want to kind of add back in here somewhere, okay? The purpose of a word equation is to get rid of extra information that we don't need that isn't important to us. It's a way for you to kind of get rid of that extra information you don't need. For us, gas is an extra piece of information that we really don't need to be able to write and balance this chemical equation. All right, our last example is methane is burned with oxygen, because you can't burn anything without oxygen, right? One of the ways to put out a fire is to smother it. Producing carbon dioxide and water. Okay. So again, that's our sentence. This is our final example. So again, the parts of this that are become symbols, okay, that is burned with, producing, and, right? The is burned with is going to become a plus sign, because that's telling us there's another reactant. Producing is going to become our arrow, and again is going to be a plus sign. So we have methane to give us our word equation. It's methane plus oxygen, arrow, carbon dioxide, plus water. All right, that concludes our notes for today. I apologize that they were a little bit longer because they had that review in there. That review is really important though. So, your first homework assignment is on page 211, number 9. Probably the easiest way for you to do homework is going to be to write it on a piece of paper, take a picture of it with your cell phone or some sort of camera, an iPad, something, and then upload that picture for the assignment in Google Classroom. Remember, if you are a packet learner, so you're learning from a packet, you could try to use Remind to send it to me, or if you do have a cell phone and Remind doesn't work for you, if you somehow reach out to me by email or something, I probably would give you my cell phone number so that you could text me a picture of your answers. But I'd rather not make my cell phone number readily available. So homework number 1 is due tomorrow. Thank you. Have a great day, and I will see you guys, or not see you guys, but I will talk to you guys tomorrow.